The puppy out?
Yes, please do. Hey, guys, I just need a minute to get set up here. JT's gonna let the dog out here. And JT, if you are able to grab an iPad cord for me. Oh,
I don't know how to carry a knife. Sorry.
yeah, you don't know how to carry a knife. David needs me to cut an apple for him. So I'm gonna
Big
cut
knife.
an apple. David, you can say hi to everybody. Did you wash this apple?
Yeah.
Okay. Yeah, right now it's just. What do you need me to get for you? I need a cord for my iPad. Oh, get
Like it?
Charlotte away from this knife.
Like it?
Yes, please.
Oh!
All right, there you go.
Seeds.
You can take care of that. Here, take this knife carefully back in the kitchen. All right, guys, I'm gonna get my iPad set up here. And then we will go through this practice exam. Hi, Charlotte. Hi. You want to come up and say hi? Here, we'll let Charlotte say hi. Come here. Come here. Oh, Charlotte can say hi. Here's Charlotte. Anybody even there? There's two people who are there. Why is there only two? See, she said hi, Charlotte. Sometimes a lot of people might watch this later. No, you can get it out, and you need to then
Get
Scooty. Yep.
let's get out of Scooter.
Yep. Yep.
Don't touch my needle.
Okay. Yeah, that works, JT. Thank you.
You just want us to go and get ready?
Yep. You guys can go get ready for bed. All right. Can you guys hear me okay? So I saw Sarah, you were commenting in the chat. Lauren, can you hear me okay? All right, very good. All right, so just give me a second to finish getting things set up here. And I might need you guys to feed the cats and Charlotte, please. All right. So let's see, I'm going to actually put in here too, so we can just kind of talk about it, the study guide, just so that I'm going to walk through that first and kind of give you guys a little bit of an overview of how to think about different problems and so forth that you might see here. Apple pencil. If you guys have any questions too about things as we're sort of starting out here, you can feel free to put them in the chat if you don't want to unmute. All right. So just take a second here and we'll go through some details on this study guide before we kind of go through the practice exam, just to make sure if there's any questions here, I can sort of address them. So again, Unit 3 and Unit 4 are what comprise content for this exam. So some topics from Unit 3, the sort of the big picture thing is thinking about stoichiometry. All right, no problem, Lauren. I see your comment here. And so the big picture thing is that you're going to see a problem on stoichiometry. In particular, I would make sure that we understand how to do a limiting reactant problem and how to use ICF tables. So we'll kind of go through a problem today that sort of practices that. You don't have to use ICF tables, but these again are a way to determine after you sort of do chemistry, you might have some information about trying to think about who might be left in solution. How much might you have left of your reactant that was not limiting? So thinking about some topics from this first learning unit, learning unit 3, talking about mole and chemical formulas. So there's going to be some simpler problems that just have you do like single unit conversions that use Avogadro's number, that use molecular weight, thinking about mass percent, thinking about how to determine empirical and molecular formulas. And so those are going to be kind of some of your simpler problems, and we're going to have some that we'll go through on our practice exam here. Then we have balancing equations. There you will see kind of a question that's just the simple skill of can you balance an equation, but then that might become an integrated skill or an embedded skill as we work through some questions in part 2, where you have to create and then balance an equation in order to use it. And then the last thing that we did in unit 3 was thinking about making solutions, doing a dilution with solutions. So this is an equation that will be on your equation sheets on the front part of your exam. And then using molarity. So using molarity is another way to kind of get us to moles. So that's content from unit 3. The big thing where you're going to see your part 2 problems is doing stoichiometry. Everything else that you sort of see up here and then here, you're going to see mainly in part 1 type problems, but it may be something that gets embedded in a calculation that you'll see in part 2. Now, thinking about our 4th skill, this is where we actually had 5 separate lectures that we sort of had on this. There was writing aqueous chemical equations. So there is a problem where you have to kind of write me a balanced molecular and then a net ionic equation. Even though total ionic was a piece that we've practiced, it's not something that I'm going to have you do on the exam, but you want to be able to think about all of the pieces that are in solution, because you need to remove spectator ions to write your net ionic equation. Thinking about whether things are strong, weak, or non-electrolytes, and that actually relates a little bit to our acid-base sort of piece too, thinking about whether we have a strong or a weak acid or base. And then with precipitation reactions, that's one of those ones where you need to predict what the stuff on the right side of the equation is going to look like. You are provided with that table 4.1, which are the solubility rules. And then acid-base reactions, being able to predict what happens there. Again, that's knowing that content from table 4.2, who's a strong or a weak acid or a base. And remembering when we have carbonates or sulfites, we're going to see some unique chemistry with those. Oxidation reduction reactions, I would say this is largely a part 1 type of a thing, where you're going to be asked to identify oxidation numbers for species, telling me who's oxidized or reduced in a chemical reaction, or qualitatively kind of giving a name to the kind of reaction that you see. So it's more of like a type 1, or I should say a part 1 type problem. And then we just did gas chemistry today. So there's some aspects that might be more part 1, this qualitative piece, being able to think about what phase of matter might be, or sort of qualitatively predicting what might be happening as you adjust the temperature, pressure, volume, or quantity of a gas. So being able to think about that qualitatively might be something that you'll see in part one. But I sort of already did tell you, I'm sort of giving you a heads up here of the kinds of problems you're going to see in part two, right? You are going to see a more involved stoichiometry problem, and you are going to see sort of a gas law problem. We're going to need to use PV equals nRT. We did these two problems in class today, whether it's an unknown variable problem or a changing variable problem. So those are kind of two of the larger problems that you're going to see in part two, and kind of highlighting that with unit 4, you know, all of our previous skills kind of become embedded, you know, the ability to convert chemical names to formulas, determining molecular weight, writing and balancing equations, and then doing stoichiometry. So those, all of these skills continue to build, and sort of the understanding and expectation is that as we move on, that these things will become skills that you just are familiar with and know how to do. So I'm going to pause there for a second. I don't see any questions or comments right now in the chat. The second page here was just, there wasn't anything new on this part. Actually, this should say exam 2 study guide up here. There wasn't really anything new that was on this second page here. It's kind of highlighting that what I think are good study strategies. Look back through the problems that we did in class, right? That's a good representation of the kinds of problems you're going to see on the exam. Go back and work through the problems that we have in our problem solving sessions. Again, we always record these, and video links are available. I tend to work through problems. Usually the problem solving sessions might have some problems that are a little bit more challenging than you might see on an exam, but I always feel like I'd rather have us practice things that are harder than what you're likely to see when you have to do something solo on an exam. And then, you know, on all of those skill sheets, right, there's always like laundry lists of problems that you can work through. If you ever are working through ones, those are where I pull my problems from, the ones that we do either in class or in problem solving sessions. So if you happen to work on one that we didn't do in one of those sessions, feel free to reach out if you wanted to know if your solution's correct or not. And highlighting that I do have a series of videos that are available on Blackboard. Any of the problems that have asterisks by them on your skill sheets, they already have a worked out solution on Blackboard, both as a written sort of PDF file, so you can just kind of see all in one kind of the solution, as well as a walked through video solution. And because I kind of made these the old fashioned way, I started making these probably 6 years ago now. I didn't have my iPad and technology, so I literally was just kind of holding my phone, my cell phone, above a piece of paper as I was writing. So if you do watch those, you probably want to have the written PDF by you, because it might be a little bit hard to see all of the content clearly if you're just watching the video. So what I'd like to do now is kind of go through this practice exam. And what we'll do is highlight. So this was from Dr. Brown's class. He and I teach, you know, identical curriculum, and our exams are often very, very close to one another. So he provides, you know, the same information that I do, just sort of present it in a different way. So I actually have that table 4.1 that we had, but he has, you know, some useful information, some equations, things like that he has available, and we'll have a periodic table. So the nice thing with this is you won't need to have any other resources that you'll need to bring with you. Everything that you're going to want to have is actually going to be provided on that first page of your exam. So if you want, you can even just tear that off. We'll restaple it at the end so you have all of that information ready. So what I want to do right now is just spend some time kind of going through these questions. And let me just make sure to grab here. I print out. Let's see, no, I don't have it with me. That's all right. We'll just kind of work through this. I may have to, just because I don't have my handwritten notes for some of the calculation problems. I may take a quick break for a moment after we go through the first part here to go grab my answer key so that I don't have to try to do math in my head for part 2. But we'll work through part 1 here, and then we'll take a little 5-minute break here while I grab that. And let me plug in my iPad here so it doesn't die. All right. All right. So, and all of the problems that we're going to work through today, you'll notice that you can find sort of the corresponding kind of prompt for the kind of problem that is on the study guide. So this is one of these where we have to identify the oxidation states for the indicated elements in the following compounds. So it's not necessarily for each species, but remember how we do this. We've got HNO3. So as you're going through and practicing anything, see if you can sort of practice doing multiple skills with this, right? This would be nitric acid. So if you see something, ask yourself, is that an ionic or a covalent compound? What kind of a substance is it? So this is an ionic compound in the sense that it's a strong acid. It's what we call an electrolyte, but it really exists as H plus and then NO3 minus. So if we were identifying oxidation numbers on things, anytime we have sort of an ionic compound, if it is an ion that's monatomic, the charge on that is going to be the oxidation number. So it's going to be +1 for that hydrogen. And remember, when we're doing polyatomic ions, we have to make sure that what we have add up as the charges here add up to -1. And when I say charges, we're going to consider the oxidation numbers here. So Charlotte. So what we're going to have here is anytime we have a polyatomic ion or something that has multiple atoms together, there's usually going to be something that is going to be a given, something that we're going to know. And often that's oxygen or hydrogen or maybe a halogen. Hey, somebody's going to need to come here and grab Charlotte. If she's done eating, you might need to just let her out. Has she been out yet? She went out to go to the bathroom? Okay. But if she's done eating here, you might need to get her out because I can't have her barking here. So something like oxygen here, that's going to be something that we know. Oxygen is always -2 unless it's part of a peroxide. Okay, and that's going to be a unique situation. The only time you're going to see oxygen as something else is when you see H2O2. And in that case, oxygen is going to be -1. And then the hydrogen is going to be +1. So it's the only time you're going to see oxygen different than -2. But again, watch what we do here. We're going to have -2 as the oxidation number. There's 3 oxygens. So the sum total of the negative charge that we get from those 3 oxygen atoms is -6. We have to have the sum total of the charge that comes from oxygen and then the charge that comes from nitrogen equal -1. So that tells us that the nitrogen contribution to charge has to be +5. And since there's only one of them, nitrogen is going to have a +5 oxidation number. Okay, so they say oxidation states here, that's the same as oxidation number. So just a formalism, I want to make sure that everybody understands that those are referring to the same things. So this is going to be 5. Again, if we're looking at iron here in iron phosphate, so iron phosphate is going to be iron, and we can see here that it's going to be a +2 charge because we've got our phosphate that's -3. So when we do our sort of crossover approach, that's how we get Fe3PO42. Somebody needs to let Charlotte out, please. She's ringing the bell. So again, this one's actually pretty easy for iron because if you have a monatomic ion, it's basically the charge that's on it, that's the oxidation number. So it's going to be +2 here. And if you don't write the plus, that's okay. Obviously, if there's a minus, that has to be there. If there's nothing there, then we consider it to be a positive. Let's go to this next guy down here. So we've got the sulfur in this sulfite anion. Okay, so a sulfite anion here. So let's take this guy over here, and we're going to have SO3, 2 minus. So if I do my same approach here, I'm going to have my oxygen as -2. So it's going to give a net of -6 for my oxygens. And just like we saw with nitrate, we're going to have that sum charge equal to, in this case, -2. Sorry, I can't write here. So that means this sulfur is going to be +4. So it's going to be +4 there for our sulfur. Okay. Last guy here. This is one of these things that this is how we find hydrogen in its pure elemental form. In its pure elemental form, anything has an oxidation number of 0. Okay, so anything that is as you'd find it in its elemental form, you're going to see an oxidation number of 0. So I'll always pause here at the end. If any of you guys wanted to write something in the chat, I'll give you a second to sort of think about it before I move on.
I have a question.
Yes.
So the pure elemental form, I know the mnemonic of have no fear of ice cold beer, and all those are the diatomics. But
Okay.
there's a problem in something else we did where it was an aluminum and it didn't have a charge on it, and you said it was neutral because it was in its elemental form. And I guess I don't understand how you know when a metal is in its elemental form.
If it's a solid and there's no charge on it, then it's in its elemental form.
Okay, so if it's written down and there's no charge indicated,
Yes.
then we can assume it's in its elemental form.
Yep.
Okay.
So if it's not part of an ionic compound, that's a really good kind of question. So, and I'm going to write that down. Have no fear of ice cold beer. Is that what it is?
Yeah.
That's funny. Okay, so we've got hydrogen gas, nitrogen gas, fluorine. So, and I'm thinking in the periodic table. So we've got nitrogen, oxygen, and then here's all the halogens. We've got fluorine, fluorine, bromine, iodine, and then we've got nitrogen, oxygen, and then hydrogen gas. All right, I like that.
But
Now,
any of those that come as a diatomic, they're neutral.
Yes. Yep.
Okay.
Yep. So if you see something that either comes with a charge like this because it's a polyatomic ion just written separately, or here, you know, there's a polyatomic ion, but in this case, we're talking about the iron. But yeah, if there's a charge that's on it, it's not in its pure elemental form.
Okay, if it's just like hanging out by itself and there's no charge indicated, it's just neutral. Okay.
Right. So keep in mind, like if I were to give this guy Al +3, then the oxidation number would be +3. Okay. If all I had was aluminum, and then with or without solid, if you just saw aluminum, then it would be 0.
Okay. But if it's part of a compound, then we can assume that it has a charge.
Correct.
Okay.
Yep.
Okay. Thank you.
Yep. All right. So just like we did in class, this next problem asks us to sort of put these pieces together and consider a redox reaction and identify who's been oxidized and who's been reduced. And in this case, what we need to do is go through and identify oxidation numbers on things, tie together things that have changed, and then ask the question, is that change indicating an oxidation or a reduction reaction? So hopefully it's pretty straightforward to see that the two reactants that we have here are 0 for their oxidation number, because they are how we would find these in their elemental state. Reminding us here too that when we have things here that have coefficients, that's important for balancing the chemical equation, that being important for doing stoichiometry, but that's not going to be important for thinking about oxidation numbers. Those coefficients don't have anything to do with that. Now, when we go over onto the right side here, we've got an ionic compound that's going to have a -2 oxidation number for the oxygen, and then a +1 for the sodium. Remembering, if we have an ionic compound, the oxidation numbers are simply the charges that we have on the cation and the anion pieces. So now that we see these, I'm going to tie together things that are changing their oxidation number. And when we see something that decreases their oxidation number, okay, that means that we have gained electrons to do so. And again, going from 0 to -2, we had to have gained negative things, gained those electrons. And so gaining of electrons is reduction. And correspondingly, a redox reaction is going to have something where we lose electrons. So in this case, we're increasing our oxidation number. We have the loss of electrons, and this is going to be oxidation. And you'll notice here that it says give the identity for the element that's oxidized and the element that is reduced. So in this case, they actually start as elements for our reactants, but even if it was something that was a compound, you always want to be identifying the specific element that is oxidized. So we had a few examples in class, maybe where we had like nitrogen dioxide, that last problem that we actually went over today in class. NO2, it's not that NO2 is oxidized or NO2 is reduced. It's one of the specific elements that's part of that. Okay, so in this case, when we think about what's oxidized, we're just going to put that the element oxidized is going to be sodium, and then the element that is reduced is going to be oxygen. Now, I probably would give you credit, I wouldn't take this off if you put O2 down, but keep in mind, this is just asking us for the element. It's not asking us for the substance, because often it's not necessarily the substance that's oxidized or reduced. It's an element within that substance that's oxidized or reduced. So I'm going to pause there for a second, see if you guys have questions on this. I will say one other thing that I am likely to ask on a question like this, because we have covered it in class, is I might ask you to identify the type of reaction that this is. So in this type of reaction, that's where we're done identifying it as either a combination, that's what this one is, decomposition, okay, single displacement, or combustion. Those were the 5 or 4 kinds of different reactions. So this kind is going to be a combination. And just as a review, the other 3 types are we could have a decomposition. Okay, so imagine that this reaction, we're going in the reverse direction where we're going to take Na2O and we are going to make it into oxygen gas and sodium solid. That would be a decomposition reaction. We're decomposing something and making it into smaller or more pieces. Combination is we're combining things together. And a key to all of these redox reactions is often something is present in its elemental form. Okay, so we've got combination and decomposition. We've got single displacement. And I'm going to move my stuff over here. I didn't give myself enough room to write single displacement. Okay, and then we've got combustion. So just doing a little bit of review on both of these. Single displacement, unlike precipitation reactions and then acid-base reactions, those are ones where we're swapping partners. That's a double displacement. Single displacements are always going to have something that starts out as in its elemental form as a reactant, and then something in it is in its elemental form as a product. So you're kind of changing by sort of displacing who gets to be in their elemental form. So that's how you can identify a single displacement reaction. And then a combustion reaction is always going to have some type of a fuel or something that you react with oxygen. Okay, and that's a combustion reaction, and we generate carbon dioxide, water, and energy. Okay, but combining with oxygen is going to be a combustion reaction. Okay, any questions on that guy? All right, so this is a problem which I'm going to tell you I would expand on a little bit because this asks you to think about strong, weak, or non-electrolytes. So we are going to do that, but I'm going to highlight that I'm going to be asking you to think about whether things are strong acids, strong bases, weak acids, weak bases. Okay, so that's going to be something else to think about. Now, I want to highlight that things that are strong acids or bases or salts are going to be strong electrolytes. Things that are weak electrolytes are going to be weak acids or bases. Okay, and just highlighting, when I say salts, I mean an ionic compound. And things that are non-electrolytes are going to be covalent compounds. So that's another way to sort of look at this and think about this. Okay, so in this case, this first one, we have a weak acid. So this is going to be a weak electrolyte. Okay, we've got CaCl2, that's an ionic compound. Okay, so that's going to be a strong electrolyte. We've got KOH, which is a strong base. So again, we identified strong bases are strong electrolytes. And then we've got a molecular compound. Molecular compound, that's another way of saying we have a covalent compound. Okay, so this is going to be a non-electrolyte. So again, these questions could be asked in a couple of different ways. I could ask you to identify strong, weak, or non-electrolytes, or I could ask you to identify if it's a strong acid, strong base, weak acid, weak base, ionic compound, covalent compound. There's lots of ways that I could ask you to think about these. Okay, but one of the things that I did tell you is I'm going to ask you to know your strong acids, strong bases, weak acids, weak bases. So you would not have sort of this descriptor piece here, because those are things that I would expect you to know. The one weak acid that we talked about was acetic acid. That's what that guy is, okay? The one weak base that we've talked about is ammonia, NH3. Okay, and we talked about the things that form strong bases are anything from a group 1 metal hydroxide or the bottom part of the group 2 metal hydroxides. Okay, molecular compounds are going to be covalent compounds. So pause there for a second, see if I didn't see any questions come in the chat, but see if Sarah, you or Lauren have anything. All right. So I forgot actually this exam here, this practice exam starts a little bit sooner with what we have here with some calculations. So I'm going to run upstairs real quick and I'm going to go grab my my key. I think I left it upstairs here. Just checking my computer bag here. All right, I'm going to pause. Give me about 5 minutes and then I will be back here and we'll continue. right, I am back here. Let me plug my computer back in here. All right, so I know Caitlin had asked the question today in terms of the breakdown of the exam. And so I wanted to make sure to highlight that it's not a 2-page, the exam is only 4 pages, but it's not an even split between sort of part 1 and part 2 kind of problems. There actually are more problems that you can get you earn partial credit for because they're more computation based. So it's more like we have with this exam where there's actually 3 pages. David, can you let her out? She's ringing the bell again. She's already been out. I know, David, but maybe she came in too soon. Can you let her out, please? Thank you. No, she's got a hat and that's why she wants to go out. Oh, she has a hat and that's why she wants to go out? Yeah. All right. So we've got 3 pages of problems here that are essentially more computation based or more something that you can earn partial credit for. So however you want to view that, if it's a good or a bad thing, but there's going to be more problems that are a little bit more involved, but will be the opportunity to earn partial credit. So this problem here, it says strike anywhere matches contain the compound tetraphosphorus trisulfide, P4S3, which burns through the following reaction. So we've got that reaction shown there. Okay. What volume of sulfur dioxide gas measured at 725 torr and 32 degrees C is produced from burning 5.64 times 10 to the minus 3rd moles of P4S3. Okay. So a lot of times when students have these problems, they're like, I don't know what to do with this. But think about this. All right, I'm looking at this problem and it's like, I see stuff here that it tells me I want to answer the question, what volume of sulfur dioxide gas? So the only thing right now that I know that I can do something with volume of gas is PV equals nRT. And if I could figure out the volume of gas, if I know the number of moles of gas, the temperature that the gas is at, remember that R is a constant that's provided for me, and then the pressure of the gas. Well, hey, look at this. Pressure of the gas. They gave me the pressure of the gas. Temperature of the gas. Oh, they gave me the temperature of the gas. And you know what? I can get, and change colors here, I can get the quantity of gas, okay? Because I can do some stoichiometry with what I have here. So one of the things that happens as we continue to advance on and learn more skills and learn more kinds of different things we can do with chemistry, it's almost like you've got like a deck of playing cards that are all different actions that you could do. And the key to being successful in chemistry is knowing how to string these actions together. So part of this problem is saying, you know what? If I had some way of figuring out the number of moles of gas that I have, then I could use the ideal gas law and I could do this calculation that's essentially the equivalent of an unknown variable problem, and I could figure out that volume. Okay, so I know it's sometimes challenging trying to put these things together, but that's kind of where we're going with chemistry here. So let's see if we can work out how to do this. We need to do the stoichiometry piece first because I can't solve my unknown gas variable problem unless I know all 3 of those unknowns. The quantity, N in moles, the temperature and the pressure are given, but I need to figure out that volume or that quantity N in moles. So let's go ahead and do that. So I'm just going to rewrite this equation here because this again is how I like to tackle doing my stoichiometry problems. Is I like to put the pieces of information that are provided sort of underneath my equation. So in this case, they told me that I had 5.64 times 10 to the minus 3rd moles of this. Now we're burning it. So it's not explicitly said, but because I'm burning it in the presence of oxygen, there's lots of oxygen in the air. It's implied that this is an excess. So this isn't a limiting reactant problem. And they actually gave this to me in terms of moles. So I don't even need to do anything to get that to moles, right? They gave it to me as moles. I can use my balanced chemical equation then to directly relate this to the number of moles of SO2. And then I have what I'm ready to use in my unknown variable gas law problems. We're just going to move this over a little bit here, give myself some more room. So let's go ahead and do this calculation. 5.64 times 10 to the minus third moles of P4S3. Remember, when we're doing stoichiometry, it's really important to have a value, a unit, and a qualifier to make sure that I have the right pieces that I'm using as my unit conversions. So for my balanced chemical equation, I know that there's 1 mole of P4S3 that are going to react and produce 3 moles of SO2. So that tells me that I am going to have 3 times as many moles of SO2 as I started with moles of P4S3. So that is going to be 0.0169 moles of SO2. Okay, so that again is going to give me this piece, right? So that's my N there, my quantity of gas product in moles. And then I'm going to take and I'm going to put this guy right in here. And they gave me these 2 pieces. So as long as I make sure that those are in the right units, I'm ready to go. So here's where we have to make sure to remember from today's class, what are the units that we need to have for these? So I'm going to treat this like I did this morning when we had our, I should say this afternoon, when we had our unknown variable problem. Okay, I'm going to write down all my pieces, PV, NT, okay, pressure must be in atmosphere. They gave it to me as torr. So 725 torr. I'm going to use a little unit conversion. 760 torr is equal to 1 atmosphere. And so in this case, I'm going to have, let's see, 0.954 atmosphere. Okay. My volume, okay, is what I'm interested in finding. So that's my unknown, right? And I solved my equation here for that guy. So I'm gonna use that here. My N, I just figured out, right? So that's 0.0169 moles. I just figured that guy out. And my temperature is 32 degrees C, but remembering that it needs to be in Kelvin, I'm gonna need to add 273 to it. And then I get 305 Kelvin. Okay, so now I'm ready to actually put these pieces in, and I've sort of run out of room here. So I'm going to actually go right up there and put those pieces into this equation here. So I'm going to have 0.0169 moles. Okay, I'm going to multiply by the R gas constant, which is 0.08. And I told you guys in class, I apologize for this, depending on sort of what problem I've done and what kind of my answer key is that I'm using, whether it's one I made early or late, I might have 2 different versions of this gas constant. One is just a rounded to 3 sig figs unit of the other one. I used that one today. I'm going to use this other one, 0.08206. The one I used today was 0.0821. Okay, either one is going to be acceptable. You can use the one that you're going to have on the front of your exam, which is going to be the one with more significant figures, 0.08206. But either one of those is going to work fine. And I have run out of room here, so let me slide things over here. Just giving myself some more room here. Move these pieces over. Okay, so units for this are liter atmosphere per mole Kelvin, and then times temperature, which is 305 Kelvin. Jeepers, I apologize, I'm getting super tiny here. Pressure is 0.954 atmosphere. Okay, now looking at units that cancel, moles cancel, Kelvin cancels, atmosphere is going to cancel, and I'm left with units of liter there. Okay, go through the math. this ends up being 0.444 liters. That's going to be my answer. So lots of work to do on that problem, but there wasn't anything that specifically, or I'm sorry, there wasn't a lot of room there to do that problem. I don't know why my, oops, hang on a second. Maybe that's why. Maybe it was just on my end. My screen seemed to be jiggling a little bit there, but I think I fixed it on my end. So I'm going to pause there for a second. There was a lot of pieces to that problem. It had kind of had a built-in stoichiometry piece. It had a gas law piece, okay? But you're going to see, you know, a couple of problems that are on these calculation parts that are going to ask us to put multiple skills together. So I'm going to pause for a second there to see if Lauren, you or Sarah have any questions.
Are we just going to have to memorize like what R is and like the
No.
conversion?
So you are given, okay, I'm going to give you this unit conversion. I'm just going to say 1 atmosphere equals 760 torr, just like we did in class. Okay, so I'll put that on the front page. You're going to have your R gas constant. Okay, you're going to have PV equals nRT. So you're going to have these equations, you'll have the constants, but it's just going to start filling up space on that first page of your exam, the one that you can take off that kind of has your name and the periodic table and all of it with it. So you're going to be given this number. Okay, I'm basically going to say that it's a useful number. I'm not going to tell you what it is for, but it's like, oh yeah, 273. That's how I convert Celsius to Kelvin.
Okay, good. I was worried I was going to have to like memorize like R and all that.
Nope. Even equations and stuff like that, they will be provided for you.
Okay, great.
Let's see. So Lauren, you do not need to know that 760 torr equals 1 atmosphere. And it looks like, yeah, 0.443, that's going to be, you would not be marked wrong. That's certainly close enough. It's a matter of a rounding issue or things like that. So that's totally fine. And you do not need to know that 760 torr is 1 atmosphere. I will provide that for you. All right. So let's move on to another problem here. Kind of related in that it's you know, another one of these computational pieces. Okay, so this tells us that the detonation of liquid nitroglycerin proceeds as follows. So they give us a balanced chemical equation. So if we have 3 grams of nitroglycerin that react completely, how many moles of water would be produced? So hopefully you see that this piece is kind of a stoichiometry problem. They give us some molar masses. So I'm not going to kind of rewrite this problem right there. I'm going to kind of write stuff underneath it as though it was sort of part of it. They give us 3 grams of nitroglycerin. So we've got 3 grams of this guy, and we want to know how many moles of water are going to be produced. So I'm going to sort of write over my stuff here, but if we think about doing our walk, I can use molecular weight to convert grams of nitroglycerin to moles. I can use my balanced chemical equation to change who I'm talking about. And that's actually the answer that I want. It's not even that they're asking how many grams, or since this is a gas, just as a little kind of preview, I could ask, you know, what would be the volume of gas that could be produced if I was, you know, I'd have to give you some temperature and pressure sort of considerations, or I could say how many grams of water are made, and then you'd need to use molecular weight. So lots of different ways that we could kind of make these problems a little bit different. But what this problem is doing is literally just asking us to do a 2-step stoichiometry walk. Okay, so not super involved, this problem here in terms of the calculations. So again, we're going to have 3 grams. I'm going to just call this nitroglycerin NG. And I'm fine if you want to do that. Just kind of let me know what you're labeling things. We don't need to spend a lot of time writing our qualifier piece. You can give an abbreviation for it. And in this case, I know that 1 mole of nitroglycerin, right, is 227.1 grams of nitroglycerin. And then I'm going to know that I've got 4 moles of nitroglycerin for every 10 moles of water that's produced. And that's all that I need to know for my calculations. It was only a 2-step walk. So there's only a 2-part unit conversion. Work out the math for this, and it's going to be 0.330 moles of water. And just sort of highlighting, here's a couple of ways that I could make this problem be a little bit more involved, if you will, right? And actually the second part of this asks us to expand on this. So we're going to do that in a second, but I could ask you how many grams of water, right? In that case, you'd use molecular weight. I could ask you something about the volume of water that's produced. And if I gave you the pressure and the temperature of that water, then we could use our ideal gas law to figure out the volume of water that was produced, okay? Or another step, which is actually the part B of this problem, is asking how many total hydrogen atoms are contained in the amount of water that we have, okay? So note, I could go from moles of water to number of water particles using Avogadro's number, but still that's not going to get me to hydrogen atoms. So see if you can see how we get this last little piece in, okay? So I could take this answer that I have, 0.0330 moles of water, and then I can use Avogadro's number. That is also a number that will be provided for you. And Lauren, to address your question here, scientific notation would be totally fine. And yes, if we're going to have 3 significant figures, that would be 3.30. And that is what we'd have here because we were given 3 significant figures in the 3 grams that we started with. Yep. So 1 mole of water is Avogadro's number, 6.022 times 10 to the 23rd. Molecules of water. Now, if I was to stop here, I would get the number of molecules of water. But this problem is asking us about the number of hydrogen atoms that I would have. So in this case, I'm going to say for every 1 molecule of H2O, notice this is not mole of water, it's every 1 molecule of H2O, there's 2 atoms of hydrogen, okay? So that's actually going to get me to be double of what I want here. And why is I am not charging here. Hang on 1 second. I don't want my computer to die here. There we go. Now I'm charging. I didn't realize we weren't plugged in there. We should be good now though. Okay, so mathematically work through this and we're going to get 3.98 times 10 to the 22nd hydrogen atoms. Okay. So this problem actually sort of split it out in terms of a part A and a part B. So it's like, okay, part A is doing some basic stoichiometry. And then the part B is like, okay, can you take that 1 step further? And here kind of shown in red here are some other ways that you could take that simple stoichiometry and go 1 step further. So I'll pause there for a second, see if you guys have questions. I think you guys asked a couple as we were kind of going along there.
I don't know why, but I get 3.98 times 10 to the negative 24th.
So let's see, if you're taking 0.0330 and you're multiplying by 6.022 times 10 to the positive 23rd.
Okay.
Right, so my numerator,
Mm-hmm.
so that might be it. So try that again and let me know if that's not.
Oh yeah, that fixed it. I don't know why I accidentally hit the negative in there somewhere.
That's all right. Okay. Next piece is asking us to think about empirical formulas and molecular formulas. So this problem is actually not super involved. It actually doesn't take a ton of work to work through this problem, okay? So one of the things to remember, and as we think about when we did these, we've got a molecule that has, and let me kind of break this down a little bit. When we talk about a molecule, that means that we've got a covalent compound. Okay, and that covalent compound can have an empirical formula. And the empirical formula is the simplest whole number ratio. And I don't feel like writing all of that out, so I'm going to call it SWNR, the simplest whole number ratio of atoms. Okay. Ionic compounds only have an empirical formula because that is the simplest whole number ratio of atoms. So it's only covalent compounds where there might be a difference between the empirical formula and then the molecular formula. And so the molecular formula, and I'm kind of writing over the spot for my answer here, but that's okay. The molecular formula might be some scaled up version of the empirical formula where it shows the actual number of atoms that are within that molecule. Now, the key to working through these problems is the difference between the empirical formula and the molecular formula is going to be some whole number factor. Okay, and how we find out what that whole number factor is one other piece to sort of have here is that empirical formula is going to have some type of a molecular weight, and that molecular formula is going to have some type of molecular weight. And what we're really doing is we're comparing these, and we're asking if they're the same or not, and if they're not, they are going to be scaled up by that same whole number factor. Okay, so hopefully that made sense. If kind of talking through it abstractly didn't, let's actually walk through this example with it. Okay, so if I figure out what is the molecular weight of this empirical formula, the molecular weight of this empirical formula is 30.03 grams per mole. And hopefully everybody sees how we got that. We just added up the weight of 1 carbon, 2 hydrogens, and 1 oxygen. And that's how we get this 30.03. Now, clearly we can see that this 30.03 is not equal to the 180.16. Okay, so putting this information down here, I got that the molecular weight of my empirical formula was 30.03. The molecular weight of the actual compound is 180.16. And what I can see here is that these are off by a factor of 6, which means my empirical formula has to be scaled up 6-fold in order to get my molecular formula. So if I take CH2O and I multiply it by 6, that's going to get C6H12O6. And so that's going to be the answer here. Now, we did go through some problems in class, and it's kind of a way to think about doing mass percent. So you might see a problem on your exam that actually has you do a little bit of work to get the empirical formula. Okay, so let me actually go, I'm going to flip back just for a moment here. I'm going to go back early on in the semester here when we were just starting doing unit 2 or unit 3 here. And I'm going to show you sort of a problem that we were working on that had us think about empirical formulas in that way. That was balancing equations. Okay, I think we're sort of right about here. Okay, so just as a review, these were some problems that we did where we were calculating empirical formulas. So we went from kind of, remember, the difficulty or challenge in a problem is how directly information is provided. Somebody in the living room? What is Charlotte chewing on out there? Okay. Can you do me a favor? Go get her a treat and then put her in her pen here. And then I need you to get ready for bed. Okay? Thank you. It's late. It's already after 10. So how easy or difficult a problem is dependent on how directly information is provided. So this problem was sort of the simplest, where they actually told you the number of moles. So we need to find the simplest whole number ratio of these guys. And then we needed to scale them up to have them be whole numbers. And so that was sort of the simplest. And then each problem that we worked on after this was kind of removing us.
It sounded exactly like the dog.
You weren't looking at what she was chewing
I was
on?
looking.
Charlotte was destroying one of my child's shoes. Put her in her pen and then you can go to bed. Tell her to go into her crate. Lock her up, please. The next step here was saying, you know what? What if I told you the masses that you have? Then you could use the molecular weights of those individual atoms to get to moles. And then you get the simplest whole number ratio. And then the last problem we had here was when you were given mass percents. Remembering that if you see a percent, you can convert it into a usable number by saying in every 100. Okay, so this was then saying 79.9 grams of carbon, the balance being hydrogen. Okay, and then I could use my molecular weights, should say my atomic weights, to get to moles and then to empirical formula. Okay, so just stepping back there for a second from where we were at to show you sort of the difference in the kinds of problems that you might see. This was like at the very, very end of those kinds of problems where we're basically then putting these pieces together here. So I'm going to pause there for a second, see if you have any questions. All right, next problem here, and I might need to go grab a different charger here because my iPad is, I'm worried it's going to die here in a second. So we're going to go through this next problem, then I'm going to go grab my other charger here. So this is a little bit more maybe recent in your memory because this was when we started Unit 4 here. We talked about writing balanced molecular and then net ionic equations here. So part of this first problem here is I give you the chemical formulas, but you have to write some information and understand sort of what's going on in solution because you have to provide the products for me. Okay, so if I look at what's going on here, I've got sodium sulfate as an aqueous salt, and then lead 2 nitrate as an aqueous salt. So if we think about what's in solution, and it's fine if you kind of write some extra stuff here. All that I need to have for grading is the molecular and the net ionic, but I'm going to write our pieces underneath here. So I'm going to have sodium cations and sulfate anions, and then lead cations and nitrate anions. And why that's important is I need to do my double displacement. I need to do my swapping. And the new options that I have are sodium nitrate and then lead sulfate. Now I need to do some sleuthing, and I'm going to be able to use my table 4.1 to figure out if any of these are precipitates. Well, maybe we've done these enough, or maybe you remember this from lab, but you're going to be able to identify that lead sulfate is going to be insoluble. It's going to be a precipitate. And then sodium nitrate is going to be aqueous. Let me give myself a little bit more room here to write that AQ. Okay. Now, the last thing that we need to do is recognize to balance this equation, we need to put a 2 in front of there. So for this problem, if you didn't write that there was a 1, and a 1, that would be okay. You can leave them blank or you can write 1s in there. Okay, so that's the balanced molecular equation. Now, remembering if I were to write on the right-hand side what I have here in solution, that aqueous means that those guys are still ions in solution, and then lead sulfate is a solid. What I identify as spectators here are sodium and nitrate because they're present as ions, aqueous ions on both sides. So my net ionic equation excludes my spectator ions. So I'm going to have lead, and again, it doesn't matter which order you write these in, lead 2 plus cations plus sulfate anions leads me to make lead sulfate as a solid. So this is my net ionic. And the only thing you'd have to have above is the balanced molecular equation that shows these guys on the right. Now, again, coefficients are not really relevant there. They're ones. So if you didn't even include anything over there, that would be okay. Okay. So this is a precipitation reaction. Okay. So this next guy here, we have to do a little bit more work because we have to take the chemical name that's given and create a chemical formula. So let's go ahead and do that. We're going to have lead 3 chloride. So I'm going to do this up here just so we can make sure we see. Those are our pieces that we have. So if I have to write this as a molecular, it's going to be FeCl3, and it's aqueous. And then ammonium carbonate, NH4 plus, CO3 2 minus. So I'm going to need to have 2 of those ammonium pieces and then carbonate. Okay, that's also aqueous. Well, I sort of started writing the pieces that made those on top. Okay, so now I can see what my new sort of partners might be. And in this case, I've got ammonium and chloride. So I'm going to sort of write that here. And I can already see that it's going to be 1 ammonium for 1 chloride there. Okay, and then I'm going to have iron carbonate. And iron carbonate is going to be Fe2CO3 3. And then I'm going to have to use my handy dandy table to figure out what the phases of these are going to be. And I'll go back in just a second to show you on that. It's going to be table 4.1 for you guys. On Dr. Brown's exam here, he actually has a typed out version of that same information to identify and help you realize how you'd see that lead carbonate is going to be another precipitate and ammonium chloride is going to be another species that is aqueous. Okay, so we need to make sure that we balance this guy. This one's going to be a little bit more challenging to balance because look what happens here, right? I can see that I've got 2 irons that are on the left or on the right, but only 1 on the left. So I'm going to go ahead and put a 2 here. And when I do that, now I've got 6 chlorides. So if I put 6 chlorides over here, okay, that's going to give me the 6 chlorides that I need. But now I've got 6 ammoniums. So that means I'm going to need to put a 3 here. And actually that works out to balance the 1 that I'm going to need here. Let me make that look like a 1. The 1 that I need there for iron carbonate. Okay. Just because I've written the stuff above on the reactant side, let me go ahead and write these guys down on the product side here. And then we're going to have Fe2CO3 3 solid, going through and circling and identifying things that are present as ions on both sides. Those are going to be my spectators, and I eliminate my spectators to write my net ionic. So Fe3 plus aqueous plus CO3 2 minus aqueous. Now I'm going to have to make sure to pull down my coefficients that would be in front of each of these. So it's going to be 3 and 2. And then I'm going to have Fe2CO3 3 solid. So with each of these, remember, we should still have our kind of net ionic equation be balanced, right? We should be able to take the information from kind of our molecular equation and pull things apart, and it still should keep a balanced equation. So we've got 2 irons, 2 irons, 3 carbonates, 3 carbonates. Sorry, that startled me to hear her bark there. All right, so I'm going to pause for a second, see if you guys have any questions on that. And then I'm going to go run and grab my other charger here because I'm worried I'm going to run out of battery here on my iPad. Any questions? I think we have 3 kind of problems left to work on here. All right, let me go grab my other charger here. All right, hopefully this is like a supercharger. It's going to charge this a little faster here. I didn't realize I was hooked up and not charging at all. All right, nothing in the chat. You guys okay with that one? All right, so the next one here is another one that's a little bit more calculation based. So it says if 31.15 milliliters of 0.1850 molar sodium hydroxide reacts with 15 milliliters of sulfuric acid, what is the molarity of the acid solution? So hopefully one of the things you realize is this is very similar to the problems that we that you had today on your quiz in class. Okay, this is an acid-base reaction. Okay, so here's what we're going to have here. It doesn't ask you to do this. You don't necessarily have to do this, but I think it helps us kind of put our pieces together. Let's write a balanced chemical equation for what's happening. So we know we have a sodium hydroxide solution, and then we've got a sulfuric acid solution. Okay, so when we think about what's happening with this, again, we're going to have acid-base reactions are kind of double displacement reactions. So let's write down who we had in solution just for practice. We've got Na plus, OH minus. We're going to have H plus and SO4 2 minus. So when we have acid-base reactions and we do that double displacement, we're going to be getting water, and that's going to be liquid. And then we're going to be getting, in this case, sodium sulfate. And if we go ahead and look that up on our table, we're going to see that that's aqueous. Okay, so what that means down below here is we've got Na plus, SO4 2 minus, H2O is together there. Okay, this problem does not require us to write a net ionic equation or anything like that. But if we're going to be doing something with stoichiometry, we better make sure that it's balanced. So in this case, we can already see that I'm going to have to put a 2 in front of my sodium hydroxide, which is going to put a 2 in front of my water there. So that's how we'll balance that equation. Now I'm going to write the pieces of information down that we have. Okay, so it tells us that we've got 31.15 milliliters of the sodium hydroxide solution, and they give me the molarity of that, 1850 molar. Okay, and then it reacts with 15 milliliters of sulfuric acid, and I want to know the molarity of that solution. So if I think about what's going on here, I can do a little walk here that I can take and use the molarity to convert that volume to moles. I can change who I'm talking about with my balanced chemical equation. And once I know that molarity, I can use the volume that's provided and I can calculate the molarity. So we've done a few problems like this in class. Okay, so going kind of quickly then through the calculations that we're going to have, I'm going to have 31.15 milliliters of sodium hydroxide. Because molarity has units of moles per liter, I need to convert this to liters. So 1,000 milliliters is one liter. And then I know in every 1 liter of sodium hydroxide, I'm going to have 0.1850 moles of sodium hydroxide. Now I change who I'm talking about using my balanced chemical equation. 2 moles of sodium hydroxide for every 1 mole of sulfuric acid. Okay, And then that gives me a final answer now of 2.881 times 10 to the minus third moles of sulfuric acid. Okay, so highlighting the pieces that we now have. This piece right here that we just solved for is going to be this piece, right? Remembering that molarity is the number of moles contained in a number of liters. So we just solved for the numerator of our answer. Now, they gave us the denominator of our answer, but we have to do a little bit of work to convert it to liters, and then we'll be ready to put it in here. So let's go ahead and do that down here. We can say that 15 milliliters, and I'm fine if you do this in your head if you want to. 1,000 milliliters is 1 liter, so that's 0.015 liters. So again, that is the denominator piece here. So when we're solving for molarity, molarity is equal to 2.881 times 10 to the minus third moles of sulfuric acid that's contained in 0.01500 liters. We're going to keep those significant figures. I probably should have had them over there. Molarity is equal to 0.1921 molar. Okay, problem told you to solve it to 4 significant figures, but if we look at what we were provided up here, everything had 4 significant figures. So we should have known that that was what we were solving it to. Okay, so I'm going to pause there for a second, see if you guys have any questions on that. I don't see anything in the chat, but I'll see if anybody wanted to unmute. All right, last 2 problems that are on this practice exam here. Okay, this is related to problem, I guess it was what, 7 that we did, but it's asking us just to give the balanced molecular equation. It's asking us to think about the chemistry that happens. So I'm going to write a little bit more than you need to in order to solve the problem, but just to have us sort of think about what's going on here. So if we think about what's going on, a good practice to get you into, because it's going to be important as we move into things after we return from break, is being able to think about and identify who is in solution. So if we think about who's in solution, we've got H plus and Br minus, and then Ca plus and OH minus. Okay, I've got a strong acid, and I've got a strong base. So what's going to happen here is I'm going to have that double displacement again. I'm going to form water, and then I'm going to form a salt. So this is just asking me to write the balanced molecular equation only. So we need to predict the products. So I'm going to be making water as a liquid. And then, oops, and look at that. I wrote calcium as a 1+. It's calcium 2+. And then I'm going to have calcium bromide. And that's going to be aqueous. Okay. So in this case, I need to go through and make sure I balance things. I can already see that I've got 2 Brs over there. So that's going to have to be a 2. I've got 2 hydroxides then and 2 H pluses, which means I'm going to make 2 waters. Okay. So you didn't need to write this part. If you can do that in your head, that's totally fine. But we need to recognize that this is a strong acid reacting with a strong base. That's going to give us a salt and water. Keep in mind, I think we did see a problem in class like this. It's possible that the salt that you make is insoluble. Okay. Now highlighting here, this problem actually tells you that certain things are strong acids. I am asking you to know, and that's a change from how we did things in the past, because we're going to be moving on in Gen Chem 1 and not waiting to Gen Chem 2 to do more reactions with acids and bases. We're going to ask you guys to know those right now. So knowing what's a strong acid and what's a weak acid. Okay. All right. So this next problem, They already told us that HClO4 is a strong acid, so we know that this is a strong acid. And this is a base, okay? So watch what happens here. This is a base. Notice I didn't say that it was a strong base, but strong acids is going to make H plus and ClO4 minus. This is a salt, so it's going to make Na plus and then CO3 2 minus. Now, if we do our double displacement, our swapping, okay, what we're going to get is we're going to get our salt, NaClO4. All sodium salts are soluble. I still have to go back and I'm going to show you that on that table on that first page. But you'll note here that there's 2 blanks, and maybe you remember from class, from lab, I should say, this was one of those problems you did in lab. Look what happens here. When we have H plus and then we've got CO3 minus, what that's going to generate is H2CO3. That's a carbonate. Remember, 2 of those magic ones that you need to be able to think about. If I've got carbonates and I've got sulfites, those are going to break down into water and then their corresponding CO2 gas or SO2 gas. Since this is a carbonate, it breaks down into its CO2 gas. So the other 2 parts that we have here are H2O liquid, and then we've got CO2 gas. Going through and looking at what I need to do to balance here, I see that I've got 2 sodiums on the left. So I'm going to need to put 2 over here for sodiums on the right. And that means I'm going to need to have 2 of those guys over there as well, which helps balance the ClO4s as well. Okay, questions on that guy? All right, last problem here, and then we're going to be done. We really don't have much time afterwards here. I'll see if you guys have any other questions, but we probably don't have time to run through too many more problems. But here is the last problem. We have yet to see a limiting reactant problem. You are definitely going to see a limiting reactant problem, and you're definitely going to see something that asks you to think about kind of calculating the amount of materials that are remaining, okay? So we're gonna go through, that's kind of embedded in this problem, okay? So this problem says, and there's always a story behind it. So part of what you need to do is recognize and pull away parts of the story that aren't important and pull out the pieces of information. So an early rocket fuel consists of 2 liquids, hydrazine, and you got the molar mass provided there. You'll notice here that in these problems, I'm not asking you to calculate molar masses for some of these, okay? That might be something that's an earlier question to calculate molar mass, but the assumption is that you know how to do that, and I'm not gonna waste your time or grading points on kind of getting that right or wrong. So those are gonna often be provided for you. So hydrazine, the molecular weight's given, and then dinitrogen tetraoxide, molecular weight is given. So they are reacted to form nitrogen gas and water. So there's the balanced chemical equation that's provided. You'll note that particularly at the end, these more challenging problems, I'm not testing whether you can balance a chemical equation or convert names into chemical formulas or calculate molecular weights. I want to know, can you do the meat and potatoes of this problem, which is limiting reactant calculation, and then as we'll see at the end, it's using an ICF table. Okay, so this problem says if 180 grams of N2H4 and 220 grams of N2O4 were mixed in a reaction container, how many moles of N2 gas would be produced? So I hope it sort of sticks out like a sore thumb that when I am starting with 180 grams of N2H4 and 220 grams of N2O4, that this is a limiting reactant problem. I need to figure out who runs out first. And again, whatever mechanism you use to calculate and figure out limiting reactant, use what's comfortable for you. Okay, you may have learned something else in a different class. That's fine. I'm always going to use the same format, just because for people that it is new, I want to have a consistency in what we're learning in class. So again, what we need to do for a limiting reactant problem, and I'm going to kind of write over my prompt here a little bit. I need to take each of these and use their molecular weights to convert them to moles. I'm going to take each of these and use my balanced chemical equation to figure out moles of N2. Okay, and I'm going to compare them, and I'm going to see who makes the least amount of N2, and that's going to be my limiting reactant. Okay, and that's actually going to be the answer to the first part of this problem, because it just basically asks how many moles of N2 would be produced. So let's go ahead and do those calculations. So 180 grams of N2H4. So 1 mole of N2H4 is going to be 32.05 grams of N2H4. I'm actually going to, and you'll see why at the end of this problem here, I'm actually going to stop my calculation right now just to get the moles of reactant that I have. 5.62 moles of N2H4. Okay, and then I'm going to use my balanced chemical equation to change who I'm talking about. So I'm going to have 2 moles of N2H4 makes 3 moles of N2. Okay, going through and figuring out, I'm going to grab my calculator here because I didn't figure out this one to completion. 5.62 times 3 divided by 2 is 8.43 moles of N2. Okay, so that's how much N2 I could make from my N2H4. And if I have 220 grams of N2O2, same calculation, 1 mole of N2, oh, it's N2O4. Hang on a second. N2O4, 1 mole of N2O4 is 92.02 grams of N2O4. I'm going to stop my calculation there, and you'll see why in a minute. 2.39 moles of N2O4 times, excuse me, use my balanced chemical equation. I'm going to have 1 mole of N2O4 makes 3 moles of nitrogen. So 2.39 times 3 is 7.17 moles of N2. Remember, when we're doing limiting reactant problems, it really is 2 embedded stoichiometry problems. So we have to kind of do 2 calculations, and then one of them we're going to ignore. In this case, we're going to ignore this guy because this is the guy that's present in excess. So we can't make that much. We are limited then by N2O4. And so this is the amount of moles of N2 that could be produced. Okay, you are going to see a limiting reactant problem. Okay, now keep in mind this problem could ask you to go a little bit further. It could say, what's the mass of N2 gas that could be produced? We could say something. Remember, anytime we have something with a gas, I could say, what is the volume of gas that's obtained if I gave you the pressure and the temperature of that gas? You could use the ideal gas law to figure that out. Okay, so the last little part here says, assuming all of the gaseous products escape the reaction container. So again, looking at what we have here, the gaseous reactants or the gaseous products, okay, are these guys. So assuming that all of those escape, what is the total mass of the element nitrogen that remains in the excess liquid reactant? Okay, so there's a lot to unpack there. This is a little challenging part, but you'll notice that, and I think Dr. Brown's exams might be worth 125 points. So this is a very small amount. So if you kind of get lost at the end of this and you're like, I didn't get that last part, don't worry. It's very minimal in terms of sort of the points that we have here. Let's see, with the molar mass, oh, good question. So if you're working ahead, the molar mass of N2 is actually going to be 28.02. Okay, but we'll see how we use that in just a second. Okay, so what I'm going to teach you here with this is how to think about using an ICF table. Because if we want to think about sort of what's happening here, we need to sort of keep track of things. Now, you don't have to use an ICF table. I want to encourage you to learn how to use an ICF table because those are going to be things we're going to continue to use throughout the course. So the sooner you become comfortable with them, the easier things are going to be. So how we write an ICF table is there's 4 rows in an ICF table. The top row is your balanced chemical equation, and ICF stands for the labels for those rows. I stands for initial, C stands for change, F stands for final, okay? So I'm going to write my balanced chemical equation on top. I'm going to rewrite it. So it's 2N2H4, okay? And it's not important that we write the phases right now, plus N2O4 goes to 3 N2s plus 4 H2O. I'm just going to put these phases in because it's going to remind us that it's important to think about sort of what's escaping. So these guys are both liquids. Okay, so the first row that I have is my balanced chemical equation. Do you remember how I like to write things underneath my pieces in my balanced chemical equation? That's kind of a way of setting things up like an ICF table, except my ICF table allows me to keep track of the changes that are happening. Okay, now this is why I stopped these calculations early on, because when I want to use an ICF table, and this is super important, if you're doing an ICF table, the only thing that can go in an ICF table are moles of quantities. You have to put moles in. Okay, and that's why I stopped these calculations a little bit early. So the moles of N2H4 is what's going to go here initially. The moles of N2O4 is what's going to go here. Okay, so I'm just going to put those values in. I don't need to put units in because I know that they're moles. So 5.62 and then 2.39. I'm just going to put a little note here that I know that this guy is my limiting reactant. We already figured that out, that N2O4 was my limiting reactant. Now, initially, before the reaction starts, I don't have any of these guys, so I'm going to put zeros there. Now, one of the things that I know happens, now the change row is the most important piece to kind of keep track of. When you're doing change rows in a stoichiometry problem that's a limiting reactant problem, start with your limiting reactant column. So see if this makes sense here. My limiting reactant is the guy that gets used up completely. So I'm going to lose 2.39 moles. Okay. Now I use this number then to propagate the rest, and I propagate them based on the stoichiometry inherent with my coefficients. So see if this makes sense. I'm doing this a little bit in my head because the math is easy. I know that for every 1 mole of N2O4 that's used up, I'm using up twice as much N2H4. That's what my balanced chemical equation tells me. So what I need to do is I need to multiply this guy by 2. That's how I'm going to get that I use up 4.78 moles of N2H4. Okay. Now you'll notice here, things that I'm using up, I'm going to put a minus sign here. Okay. So I've got this minus sign here and this minus sign here because these guys are reactants. They're being used up. What we do on the right side is we put plus signs, or if you don't put anything, that's fine. But I like putting plus signs to remind myself that those are things that I'm making, I'm adding to. So see if this makes sense. I've got 2.39 and I didn't finish this out. So only 2.39, I'm going to multiply by 3. We already actually did this, right? Because we knew that we were going to make 7.17, so this is times 3, 7.17 moles of N2 gas. If I take 2.39 and multiply by 4, that's how I'm going to get 9.56 moles of those gases, of water gas. okay? So the change row is probably the hardest one to do because you sort of have to do like mini mole to mole conversions. You're changing who you're talking about using your coefficients from your balanced chemical equation. Now the final row is pretty straightforward. Your final row, you basically add your initial and your change rows, okay? Now you'll notice your limiting reactant should always be 0. By definition, you use it all up, okay? This case, I'm going to be making 7.17 moles of N2 gas, 9.56 moles of H2O, and I'm going to have 0.84 moles of N2H4 that's left. Now, the problem tells me that these guys are going to escape to solution. So these guys, I shouldn't say to solution, these guys escape to the environment. They escape the container. So they're really not applicable to anything that we're going to be considering. This guy is the guy that's important because the problem asks us to think about the mass of nitrogen, elemental nitrogen that remains in this excess reactant. Okay, so let's see if what we're doing here makes sense. And I just somehow lost power to my iPad here. I don't know why. Let me try plugging this back in again. Yep, there we go. Okay. We're almost done here, so it's probably okay. But I'm going to start with the answer that I have here. Okay. So I'm going to think about how much actually remains. So that's using a calculation based on this. So I've got 0.84 moles of N2H4 remaining. Okay. And then I'm going to say that for every 1 mole of N2H4, there are 32.05 grams of N2H4. Okay. Let me actually run through this calculation really quick because I have some notes here and I can't remember. I think I stopped for a moment. Okay, that's what I had done. Okay. So, and I have to do one more thing here that I have to say for every 32.05 grams of N2H4, there are 2 times 14.01 grams of nitrogen. So I have to do this last little piece. So because not all of the N2H4 is nitrogen, okay? So if I stopped at this part of the calculation, that would tell me how many grams of N2H4 that I have left. That would tell me the mass of N2H4 that I have left. But I want to know not the mass of N2H4, of that mass, how much of it is nitrogen. So this last little piece might be the piece that people get stuck on a little bit, but said another way, if I actually were to do the calculation for this number, let me do this here in a different color here. This number is 0.874, okay? What this means is that N2H4 is 87.4% nitrogen by mass. So it's kind of a scale down factor of, hey, that first part of the calculation tells me the mass of N2H4 that's left. If I want to know that contribution from nitrogen, only 87.4% of it is accounted for by nitrogen. So finishing out this calculation, I get 23.5 grams of nitrogen. Wow, that last problem was a little bit intense, okay? So the limiting reactant piece hopefully didn't trip you up too much. That was the part A part here. But this last little piece and using an ICF table and trying to do a few calculations to figure out some parameter about something that's left after a reaction, you are going to see something like that. Now, whether it's something unique here, like how much of a certain element is left, or maybe I might ask you something about the water that escaped and tell me the volume of water that escaped, right? You could then take this number of moles, and you could use PV equals nRT to take that and figure out the volume that escaped, okay? So you are going to see sort of a problem at the end here that's going to really ask you to kind of pull stuff together. So I'm going to pause here for a second. I don't see any questions in the chat, but you guys have been with me for a while here, Lauren and Sarah, you know, to kind of get through and walk through this exam. So I'll pause and see if you guys have any questions.
This is just going to be hard to finish in an hour, 50 minutes.
Yes, I mean, it is. So, you know, strategies maybe for pacing yourself, but different people have different strategies. Some people like to start kind of in the back with the problems that they know are going to take a little bit longer to think about. Some people are like, hey, I don't want to lose the easy points on the first stuff. So, you know, for some people, it might be a balance of saying, you know what, I'm going to start with that early stuff, but I'm going to budget myself at 15 minutes. And if it doesn't come to me instantly and I can kind of work on it, I got to put it to the side because I want to save myself. And keep in mind, even though we do say 50 minutes, I pretty much do let you guys kind of go almost right up to the next class. So you might have about 55 minutes, but if you budget 15 minutes and say, I'm going to try to get through that first stuff, that rapid fire sort of stuff, and then anything that doesn't come to me right away, I got to leave for a minute because I got to go work on my calculations. That might be a good strategy. But part of becoming proficient at chemistry is sort of getting through kind of doing these calculations. And I promise you, Dr. Brown, Ms. Erickson, and I, we all run our exams by each other to make sure that we're okay on length, that it's a reasonable expectation for a Gen Chem student to kind of get through in a 50-minute exam. So, and this was one that, you know, Dr. Brown had in a previous class, you know, mine that I've given in previous classes have been similar. His were just easy to sort of already put up, and I wanted to do something different than what I had previously. So that's why I used his here.
All right, well, that's about it. I think I know what I need to study.
Okay, so again, I've given you guys some heads up. Limiting reactant problem, you're going to see. Know how to use the ideal gas law. Flipping back through here, and I'll make sure that, you know, if you guys have any questions kind of in the next day, you can send me something via Teams. I'm trying to think of the other things that I kind of highlighted. This exam, I think, is a really good kind of representation of the kinds of things that you are going to see. And to address, Caitlin had brought up the question in class, as I looked back at the exam that I do have for you, it's not a two-page split. It really is more like a page and a half, and then 2.5 pages in terms of things that are more calculation, partial credit based versus just this straightforward, no partial credit piece. All right, guys, it is, I think, late for all of us, and we've spent 2 hours doing chemistry. So I'm going to let you guys go, and that way it takes a little while for Zoom to kind of process and give me a link to post for people. So I want to make sure I'm able to get that posted tonight. So we'll go ahead and end. And if you guys have questions, send them to me over the next kind of 36 hours before we see you for your exam on Wednesday. All right. All right, you're welcome. We'll see you guys. All right, you too, Lauren. We'll see you.